So when we last left off in our Chapter 1 notes, we were discussing factors that affect boiling point. So when we think about boiling point, we're concerned with intermolecular forces. And boiling point also depends on molar mass, which is a consequence of the strength of London van der Waal or dispersion interactions. So in this example, we're asked to draw 3 constitutional isomers for the following formula. And then we're going to rank the 3 structures that we've drawn in order of increasing boiling point. So taking a look at this example, so C3H6O. One way that we can estimate the number of double or triple bonds or rings in our molecule is to calculate the degree of unsaturation, or DU. So for example, in this case, we can calculate the DU by taking the number of carbons, which is 3, minus the number of hydrogens, which is 6, over 2, plus 1. And that would in turn give us a DU value of 1. So we have 1 double bond or ring. So from this, we can draw a few valid constitutional isomers. So first we can draw our 3 carbons and an alcohol, and we can have a double bond. Okay, that's one option that we could use. The other option would be to place our oxygen as an ether functionality. And another option would be to have an aldehyde functionality. Now, my question to all of you is, would anyone like to propose another constitutional isomer? Is there another constitutional isomer that we haven't drawn from this list? And don't be shy to use the annotate feature if you want to share another unique constitutional isomer that we can add to the list. Or you can state the functional group found in your proposed constitutional isomer. Yep. The ketone would be a perfectly valid proposed structure. Yep, that's more than okay. Perfect. Are there any other structures that we'd like to share? Any other proposed structures for constitutional isomers? So our constraints is we need 1 double bond or ring. So our other option, we could also have a cyclic structure that looks something like this. Okay, so we have these 5 constitutional isomers to work with here. So My question to all of you is, which structure or structures will have the highest boiling point? Which structures have either the strongest intermolecular forces or a structure that leads to efficient packing? Which of these five structures will have high boiling points? So I see students mentioning E in the chat. That's exactly right. E has a few things going for it. First, it is cyclic, and cyclic structures in general have higher boiling points due to efficient packing, and it's able to participate in hydrogen bonding. Okay, so structure E would definitely be one of our higher boiling candidates. What would be the next highest boiling? What would be the next highest boiling? A, yep. I see a lot of people typing A. Would you like to provide a reason for that? What's so special about A? What can A do? What leads to such a high boiling point for A? Yep, it's able to participate in hydrogen bonding. The double bond does make packing a little bit less efficient, but nonetheless, it's still perfectly capable of engaging in hydrogen bonding, leading to a high boiling point. Now, rather than filling out the middle, what would be the substance with the lowest boiling point? What would be the substance with the lowest boiling point? So when we're comparing B, C, and D, the question that we need to consider is polarity. So we have to think which of these bonds which of these molecules have the most polar bonds and by extension, the greatest molecular dipole. So with these considerations in mind, when we looked at polarity and we looked at different functional groups and their relative boiling points for different functional groups, which functional groups had the higher boiling points, the ketone and aldehydes or our ethers? And don't be shy to share in the chat. Which bond would you expect to have a greater polarization, a greater bond dipole, and which molecules would you expect would have a greater molecular dipole? So in terms of molecular polarity, whoops, one moment. If we compare and we start looking at an ether, so if we draw an ether with respect to its three-dimensional shape, we have two bond dipoles from carbon-oxygen bonds, and those dipoles can partially add together to give us our molecular dipole. Comparatively, when we look at aldehydes and ketones are planar, and we have this very strongly polarized carbon-oxygen bond. There's really a large amount of partial negative character on our ketone oxygen and partial positive character on our ketone carbon. So as a result, for ketones and aldehydes, we see generally a larger molecular dipole, as this carbon-oxygen double bond is arranged in a geometry that maximizes our molecular dipole, and this carbon-oxygen bond is highly polarized, not only due to induction, but also due to minor resonance contributions. That is why when we looked at the boiling points last class session, we noticed that the ketone and aldehyde typically had a higher boiling point than our ether. The ketone and aldehyde are very close in terms of boiling point. Generally, so for this case, we'll just group them in the same category for now. Generally, the aldehydes have slightly higher boiling points, but it's very close and it depends on your exact structure. The main thing I wanted us to get away from this discussion is that depending on the intermolecular force, whether we have hydrogen bonding or dipole-dipole, the strength of our intermolecular forces affects our boiling point, and whether we have a cyclic or acyclic structure and the shape of our structure impacts our boiling point. Does this example make sense to everyone? Do the key takeaways from this example make sense?
Yeah.
Perfect. So let's look at another example and let's talk a little bit, oops, one moment. Sorry about that. There's a small delay in the Zoom stream. Okay, so let's talk a little bit about solution formation, which, just like boiling point, is driven by intermolecular forces. So the rule of thumb is like dissolves like. So substances with similar intermolecular forces will mix. So for example, methanol and water will mix because both of these molecules will engage in hydrogen bonds. So for example, when you have your molecule of methanol, it is capable of engaging in hydrogen bonding with water. Likewise, ammonia can mix with formaldehyde because we have both hydrogen bonding and dipole-dipole interactions, while formaldehyde can only engage in dipole-dipole interactions. So we have our very polar ammonia molecule interacting with our polar molecule of formaldehyde. And this dipole-dipole interaction allows these two substances to mix favorably. So another thing to consider to elaborate on this like dissolves like idea, mixing is favorable if the strength of intermolecular forces between two different substances is similar in strength or stronger than the intermolecular forces between molecules of the same substance. So for example, sodium chloride dissolves in water because sodium chloride and water can form a strong ion-dipole interaction. And it's this ion-dipole interaction that leads to favorable solubility. Now, in general, polar substances will dissolve in polar solvents. So hydrophilic or water-loving functional groups include alcohols, aldehydes, ketones, to a lesser extent, carboxylic acids, amines, and some chlorides. Hydrophilic, these substances and functional groups typically dissolve in water or are water-loving. Nonpolar molecules generally dissolve in nonpolar solvents. Hydrophobic functional groups primarily involve carbon-carbon and carbon-hydrogen bonds. Hydrophobic, immiscible with water, water-fearing. So we can rationalize this by thinking about the intermolecular forces involved. These hydrophilic functional groups found in polar molecules. We have polar functional groups. And these polar functional groups can engage in hydrogen bonding. Okay. So examples of polar solvents. So as examples of polar solvents in general have large dipole moments, a large molecular dipole. They exhibit high melting and boiling points for their molar mass. So examples of polar solvents would be water, methanol. We call these polar protic solvents because they can engage in hydrogen bonding and they can exchange their proton in acid-base processes, while molecules such as dichloromethane are considered polar aprotic. They engage strictly with dipole-dipole interactions for the most part. For your nonpolar solvents, these nonpolar solvents have no net molecular dipole or they contain large nonpolar regions. These are your hexanes, your toluenes, your carbon tetrachloride. These are nonpolar molecules and they engage primarily in London interactions or dispersion forces. Okay, so even if a molecule contains a polar functional group, the size of the nonpolar functional group determines if the species is soluble in water. So for example, as we discussed in lab with our 4 to 5 carbon rule, as the nonpolar chain increases in size, the molecule is less soluble in water and more soluble in nonpolar solvents. So for example, acetic acid is water soluble. Once we get to around 5 carbons, we have a relatively large amount of nonpolar character. So for example, the benzoic acid that we studied in the extraction lab is primarily soluble in nonpolar or slightly polar solvents. Such as, for example, dichloromethane. Does that make sense to everyone? The larger our number of carbons, the larger our nonpolar region, the less water soluble our substance is. Because even though this functionality, even though this carboxylic acid can engage in hydrogen bonding, there's a large portion of the molecule that prefers to engage in London interactions. And as a result, the interactions of this primarily nonpolar molecule with water are relatively weak. Does this make sense?
Sorry, the reason the carbons make it less soluble in water is because the structure gets like more geometrically nonpolar, or
So the more carbons we have, the larger our nonpolar region becomes. And as a result, when we think about how this molecule will interact with different solvents, the nonpolar region, which is the bulk of our molecule, can more favorably interact with a slightly polar or nonpolar solvent, such as dichloromethane, compared to a hydrogen bonding, very polar solvent like water. And the larger this nonpolar region becomes, the more your compound will prefer to dissolve in nonpolar or slightly polar solvents.
Okay, that makes sense.
Perfect. So we're now going to take a look at a few different substances, and we're going to circle the substance in each pair that is more soluble in water. So I'll do the first one and you'll do the next two. So in this case, we have an alcohol, which can form a hydrogen bond, versus an alkyl fluoride, which primarily engages in dipole interactions. So which of these compounds can more strongly interact with water? The compound that can hydrogen bond, or the compound that can engage in dipole-dipole interactions?
The hydrogen bonding?
Yep, exactly right. So methanol would be more soluble in water. I'd like you to take a moment and I'd like you to tackle these next two examples, and I'd like you to indicate which compound in each pair is more soluble in water. So compounds that are soluble or miscible with water are relatively polar and ideally can hydrogen bond. So we'll discuss this example in about 2 to 3 minutes. And don't be shy to share your responses in the chat or to share a question in the chat or verbally. And let's try to get a few more responses in the chat, and we'll discuss in about another minute to a minute and a half. We have a pretty good consensus among all the responses in the chat, but don't be shy to share your response, even if it differs from your classmates. That can help me understand the logic behind your response, and it can help me provide more focused feedback. Okay, so let's look at these two molecules. So in the first case, we have a non-polar. So in this case, we have a non-polar polar molecule compared to a polar molecule for chloroform. So which of these two solvents would have more favorable interactions with water, which is mainly a polar hydrogen bonding molecule? As we noted in the chat, the majority of the chat selected B, which is exactly right. The polar chloroform molecule can engage in dipole-dipole interactions with water, increasing its potential water solubility. So if we compare C and D, as the students have pointed out in the chat, structure D would be more soluble in water because it's capable of engaging in hydrogen bonding interactions. Yep, so that looks exactly right. Any questions on these examples? Any questions? Being able to identify and estimate water versus organic solubility is a really important skill because it can help you design and think through common organic extractions. Any questions before we move on to the next example?
Yeah, so because for on C, where
Yeah.
we have C and D,
Yeah.
because it's less than 5 carbons, it's not like disproportionate to be able to actually perform the hydrogen bonding. Like
So,
in
so the
compared to
main thing to
example
think
of,
about in these questions, it's using the phrase more soluble. This compound, which is known as butanol, is not extremely soluble in water, but it would certainly be more soluble than the diethyl ether, simply because butanol has the same number of carbons, but it can engage in hydrogen bonding, which makes it more likely to associate and dissolve in water because it has stronger intermolecular interactions with water.
got it.
Does that make sense?
Yeah, thank you.
Perfect. So let's look at this next example. In this case, we're flipping the pattern around and we're asked to choose the solvent that each pair, choose the substance in each pair that is more soluble in hexanes. So in this case, we're looking for solubility in a non-polar solvent. So I'd like you to take 2 to 3 minutes and work on the following example. And I'd like you to tell me which substance in each of these two pairs is more soluble in hexanes. And we'll discuss in about 2 to 3 minutes. And we see a range of responses in the chat. Let's spend about another minute on this and then we'll discuss. So let's take a look at this example. So in the first case, we have a structure with 7 carbons. In the second case, we have a structure with 2 carbons. So which of these two alcohols will have more non-polar character? Which of these two alcohols will have more non-polar character?
A.
A, yep. So that's why A is more soluble in hexanes, a non-polar solvent. If we compare carbon dioxide and hydrochloric acid, Which of these molecules is polar? Which of these molecules is polar? D is polar, okay, and C is nonpolar, right? So then, which of these substances would dissolve more readily in a nonpolar solvent, such as hexanes?
C.
C, yep, exactly right. Because we have a nonpolar substance dissolving in a nonpolar solvent. Does that make sense? Any questions on this example? Okay, let's keep going then. So that's it for our chapter 1 content. We're now going to switch gears and we're going to start and we're going to begin discussing chapter 2, which focuses a lot on resonance, structure and function, and acid-base chemistry.